Hi everyone, this is going to be our first video from self-quarantine. I hope y'all are doing a good job of social distancing. We did this problem in class the Friday before we left for spring break. I know it's been a hot minute, but on the back, so this should have been the last page of the last packet y'all got from me before we left. Keystrokes are just how we do it on the calculator, and I'm going to show you how to do the one we did in class on the calculator, since about half of you were gone, if I remember correctly, from track and baseball and golf, I think it was. But, focus. Alright, so keystrokes. You are going to enter the observed and expected counts. So you want to do the counts and not like percentages or whatever it gives you, into columns. You could also do this another way, but this is the easiest way to keep it all straight. And then on your lists and spreadsheets, and you'll need to name your columns to help keep them straight, okay? And then you'll go to menu for, which is statistics, and then you'll hit 4 again for statistics test. And then you can go down to number 7, which is the chi-squared GOF, so goodness of fit. Alright, and so I'm going to show you how to do that on this. I'll use the calculator just because you can see it better. Alright, so in here, what we're going to do is we're going to go to a new document, and we won't save the old one. Alright, and we are going to add a list and spreadsheets, and this is going to be our you can make this your observed or your expected, and then this would be your expected if you did it like that. Now if you notice, it will go to regular font, and if I hit enter it will say cannot accept, and that's because this is a function for exponential or something like that. And so if you just add another letter, if you don't want to type out the whole thing, that would be an option. So we observed 32 birthdays in January, February, March, 20 in April, May, June, 16 in July, August, September, and 12 in October, November, December. Now, the whole premise of this problem was, are birthdays evenly or uniformly distributed? And so if they were uniformly distributed, and we had 80 birthdays, then that would be 20 for each quarter. So that would be our expected. Alright, and then you go to menu for goodness of fit, number 7. And our observed list was our A list. And then our expected list, we're going to hit B because it was the second column. And then you're going to hit Control, and then you're going to go down to the left parentheses to get the square brackets. Now your degrees of freedom, remember, are the number of categories minus 1. And we had 4 quarters, so that's 4 categories, minus 1 is 3 degrees of freedom. And we can hit OK. And we can see that the chi-squared is 11.2, the degrees of freedom is 3, like we put, and our p-value is 0.01069. And so what that tells us is that's less than alpha equal to 0.05, and so we would reject the null because we have enough evidence. If something only happens 1% of the time, then it's highly unlikely that you would observe that data. Alright? So, some follow-up just to clarify. If the sample leads to a statistically significant result, we conclude that our variable has a distribution different from the specified one. When this happens, start by examining which categories of the variable show large deviations between the observed and the expected counts. So we talked about this a little bit in class, but if we're expecting 20, then this one here is 12 off, this one's 8 off. So because this one's 12 away from our expected, then that one's contributing to our chi-squared the most. So then look at the individual terms that are added together to produce the test statistic. These components show which terms contribute most to the chi-squared statistic. So for the hockey players one, if we did all the work in class, but we got 7.2 for the first one, and then 0, and then 0.8, and then 3.2, for a total of 11.2. And so this 7.2 here, this is birthdays between January and March contribute most to chi-squared. And so this is the one that caused the greatest amount of change, and so that was the farthest one off. Alright, let's do one more of this goodness of fit, and then we'll be done with, I think that will put us at the end of 11.1, and then we'll do a different video for 11.2. Alright, so biologists wish to cross pairs of tobacco plants having genetic makeup, capital G sub g, or lowercase g, GG, indicating that each plant has one dominant gene, capital G, and one recessive G, meaning lower g. For color, each offspring plant will receive one gene for color from each parent. So, parent 1 passes on, parent 2 passes on, we've got our Punnett square that you learned back in biology. So the Punnett square suggests that the expected ratio of GG to green to yellow-green to albino tobacco plants should be 1:1. And so this would give us green. Both of these give us yellow-green. And this one here gives us albinos. So in other words, biologists predict that 25% of the offspring will be green, 50% will be yellow-green, and 25% will be albino. To test their hypothesis about the distribution of the offspring, the biologists made 84 randomly selected pairs of yellow-green parent plants. Of 84 offspring, 23 plants were green, 50 were yellow-green, and 11 were albino. Does this data differ significantly from what the biologists have predicted? Carry out an appropriate test at the level to help answer this question. Alright, so we're going to state, so our null hypothesis is that whatever the original stated distribution is true. So the tobacco color distribution of offspring is 1, 2. Alright, and then our alternative hypothesis would be that it is not. So we don't have to know which one's off the most, we just know that it's not what they're saying. Alright, and if you wanted to make a little table, I would highly suggest it so that you can see what we're looking at. Also, let's go ahead and name our alpha value. It doesn't state, so we'll make it 0.05. So we had observed, we have expected, okay, and you have green, you have yellow-green, you have albino. Alright, so for the green, we saw that 23 of them were green, 50 of them were yellow-green, and 11 were albino. Sorry guys, working from home is not always the best of circumstances. Alright, so we would expect to see 25%, and we had 84 total plants, so 25% of 84 we would expect to see 21 here, and we expect to see 50% here, so double that would be 42, and albino would be 25% as well, so that's 21. So there is our observed, there's our expected. So now we have to do our plan, which we still have our conditions. And it's been a whole minute since you heard them, but our test that we're going to run is the chi-squared goodness of fit test. Now we have to do random, and it is 84 randomly selected pairs. So we have our random condition met. Then you have your 10% independence. Okay, and in it, we need to know if 10 times 84, which is 850, so we are going to assume there are at least 840 tobacco pairs. And that's reasonable, all right? And then we have our large counts. This is not a normal curve, so this is not the normal, but if we have our large counts, then we can use the chi-squared curve. All right, so our large count says that each expected value is greater than 5, and we have 21, 42, 21. So because each expected value is greater than or equal to 5, we meet large counts condition. All right, so we met all 3 of our conditions. So now we have done our plan, we have done our state, so now we have to do the work. All right, so chi-squared, it's really easy to do. We're going to do our observed minus our expected squared divided by the expected. It's 11 minus 21 squared over 21. It doesn't really matter which order you put it in because you're going to square it. So we do all that, and we get that it's 6.47 is our chi-squared. Now our degrees of freedom is the number of categories, k minus 1, and we have 3 categories, minus 1 is 2. And so we'll type that in on the calculator. And if you want to go ahead and draw it out, remember that because the degrees of freedom is 2, it's going to look like that. 6.47 is here. We're trying to find this tail end here. So if we're on the calculator here, then we're going to go to Menu, 6, Distributions. This is a chi-squared CDF is what we're going to use. The lower bound is the 6.47. You can make your upper bound whatever you want, large, and the degrees of freedom will be 2. And we get that it is p-value equal to 0.039. Alright, so now that we have that, we can conclude. So, since the p-value 0.039 is less than alpha equals 0.05, we reject the null hypothesis and have convincing evidence that the color distribution is not 1 to 1. Alright. So that will wrap up 11.1, and we'll do an 11.2 video next.